Hey there, everyone. My name is Ryan Schewel. Welcome to my analytics channel. So in the project today, I have a topic that I think is very interesting and it deserves some type of analysis. So I was just thinking about this recently, global warming and the ultimate impact that's going to have on our entire planet. And that's going to be a major impact. Like people, scientists, even non-scientists are trying to understand this right now. It's so massive. I don't think we're ever going to get our hands around this, and I don't know what the eventual outcome is going to be. I'm trying to be optimistic, but you have to be realistic and somewhat pessimistic too, because right now things don't look too good. But let's see. I did a bunch of analysis and I want to share my findings with you. And even before we start, we should ask our questions. Why do we want to do an analysis of global warming? Well, there's several reasons. Try to understand the scope of the crisis, right? Try to get a handle on that if it's possible, and it may not be. Try to inform policy and global agreements and understand that better. Try to create support for climate adoption and risk planning, right? If we really can't slow things down immediately, how can we do risk planning immediately and maybe slow global warming? That could be an option, right? Try to predict tipping points and irreversible changes, just for basic scientific research and investigation. Communicate urgency to the public. I think that's very important, right? Share knowledge with other people and be transparent. Detect acceleration in warnings. Again, risk management, that goes back to risk management. I don't think we're going to reverse the problem anytime soon, but at least we can prepare ourselves a little bit better. What else? Highlight regional clusters of risks. Okay, I'll show you how to do that. I have a couple examples of that down at the bottom of this Jupyter notebook, and just overall model policy scenarios to show what might happen with or without intervention. Okay, so I've got an example about that too. So I'm going to go ahead and import the data and take a quick look at this. So Control Enter, and I shared the data source at the bottom of this notebook. If we go to the bottom, you can see where I got it from. I'll just skip down there real quick. So that is the data source. You can download that and play around with the data. And by the way, I'll share all this code with you so you can copy and paste it into your own Jupyter notebook and test the code yourself, see how everything works, interact with the code, get intimate with it, and familiarize yourself with everything. And that's how you learn, right? All my demos here that I post on YouTube are for experimenting, for learning, for teaching, for engaging, things like this, right? So this is what the data set looks like. We have a couple fields over here, the ID, the country name, ISO code. So Afghanistan is AFG. I guess it's like 2-letter or 3-letter. Maybe not, that's more than 3 letters, but these look like mostly 2 letters and 3 letters. Then we have an indicator, unit source CTS code. Not sure what that is because they're all the same. I'm not sure we even need that. Surface temperature change and some kind of descriptor. I'm not sure what that is. But then we have all the years over here going off over to the right to 2024. Okay, and you have the surface area, average surface area change. That's what that is. Okay, so I found other data sets that go back to the mid 1850s. I think I saw one yesterday, but it was missing a whole bunch of data for a whole bunch of countries. Very incomplete, very lacking in a lot of areas. So I decided to use a shorter data set starting in 1961, going up to current contemporary times. But it was more complete and more comprehensive, and you can do a better analysis. If you go back further in time into the mid 1850s, but you're missing all kinds of data because it wasn't collected for various countries, and back then some countries that exist today didn't even exist back then. So that was another thing that caused a bunch of missing data points. I just thought that this data set was more comprehensive and complete. That's why I used this one. So you can see that this is wide data. This is called wide or pivoted data. We're going to unpivot or melt the data. This is called melting data. So we have data frame.melt. That's what this does, and you choose how to do the melt. So I'm going to do it by country and ISO code 3, and I want variable names to be year, and then the value names to be temperature change. And that's what you see in these columns over to the right, starting in 1961. So we have the data frame loaded. Let's melt this. And again, melting is taking something from a long format or wide. I'm sorry, taking something from a wide format and converting it to long, right? So we take it and pivot that data. So it was wide, now we're making it long. It's just easier to work with a long format. So we're going from a whole bunch of columns and just a few rows to a whole bunch of rows and just 4 columns. Okay, so everything has just been pivoted in this respect. So we have year, temperature change, linear trend, and polynomial trend, and I'm going to go ahead and plot that so we can visualize it and see what it looks like. Okay, it looks good. And the linear trend is literally what it sounds like, just linear. Polynomial is more showing a fit to the curve. So as the data points are increasing over time, you can see the polynomial line sort of curves or bends to fit the data points a little bit better. And the linear trend is just the best fit line given all of the data points, right? But it's indisputable. It goes from the lower left to the upper right, right? So basically kind of like southwest oriented to northeast oriented. That indicates the temperature change over time from about 0 change down here in 1961 to this is percent change, so 2% change over time. So kind of substantial change, not huge, not life altering yet. But if we continue to witness these kinds of changes in the future, especially if it changes at an accelerating rate, then we're going to experience a lot more pain, a lot more severe weather patterns. And from my understanding, I'm certainly no weather expert, but global warming doesn't mean that the Earth is just automatically getting warmer, and it's certainly not getting warmer every single day. But on average, the trend is getting warmer, and that's creating more erratic weather patterns and more intense storms. So bigger hurricanes, more intense tornadoes, more flooding, more glaciers melting. There was one I saw on the news just a few days ago, which is devastating. I think this was in Switzerland. Swiss glacier collapse. So this is happening in real time. Swiss glacier collapse is a lesson in climate disaster management. Yeah, this is unfortunate. This is the one I saw. So the Earth warmed up to a point where the glacier literally collapsed and descended on this small village. Now I don't want any more things being installed here. Descended on a small village and essentially wiped out the inhabitants of that village, right? Here's the aftermath. So very devastating. And it all comes from a warming Earth, right? Rising average global temperatures. The glacier just melted to the point where it couldn't withstand this it was holding back a bunch of dirt and debris and rocks, boulders and things like that. So the glacier just collapsed in the blink of an eye and wiped out this entire village, right? And that was just a few days ago. And you see these disasters all over the place at an increasing rate, right? So this really is happening. This is not a hoax, like some people say. This is not, conspiracy theory or whatever. This is real. So I wanted to take this choropleth map. I've discussed this in a couple of my other videos. It shows changing temperatures over time. So the darker the red, the higher the average temperature. The darker the blue, the lower the average temperature. Okay, you can get that from the indication bar on the right. And that's it. So you can see overall, on average, global temperatures are changing. Canada is a dark red. It started out with blue. And Russia, which is a very cold country, typically is turning red, right? So these temperatures are increasing, and you can see the effect over time. So these choropleth maps right here, px.choropleth, we're using Plotly, is a great way to see changes in time occurring in an animated fashion here. So that's the next thing. So I want to look at a couple different snaps in time, or what's it called? Just points in time, snapshot in time. Going out now, it's 2025, so 5 years from now, 15 years from now, and out to 2100, and then just do like a linear approximation using a linear regression model. Here's my model. So I'm using this data science model, linear regression. The x variable is going to be year. The y variable is going to be temperature. So basically, this is taking this concept that we saw over here, this linear trend that we saw over here, starting in going back over, I think it goes back over time. Yeah. So we just capture all the time back to 1961, and we're making a forecast into the future. It's 2025 now, so we're going into the future up to 75 years, and we're going to make a projection using this linear regression model to what temperatures could look like 75 years from now, right? So this is 5 years from now. We could see a change of about 1.6 centigrade linear change up to 1.94 polynomial, 1.8 centigrade linear using a linear model. Polynomial model is coming in at 2.4 degrees increase in centigrade, and 2100 3.5 degrees increase in Celsius, 5.26 increase in polynomial, and that is a game changer right there. If the global temperatures go up 5.26 centigrade on average, things are going to look completely different than what they look like right now on this Earth. So definitely scary stuff, definitely. So now we're looking at an ARIMA model. So this was just, a previous one is just a regular regression model planning into the future, what's happened in the past, going back to 1961 to 2025. So whatever the math is on that, 40 plus 25, so 65 years of history going out into the future, 75 years out to 2010. Now this concept right here, the ARIMA model and SARIMA, is a little bit different. This is autoregressive integrated moving average, and this is seasonal autoregressive integrated moving average. That's a mouthful. I know it's hard for me to say that. So we're looking at these time series models, again, going back to 1961 and forecasting in a time series manner. No, not regression, not a linear regression model, but more of a time series model to understand the nuances and the fluctuations of those patterns of these little blue dots that we saw initially. So these dots bouncing up and down, that's what the ARIMA and SARIMA model is trying to capture and report on. So we can see back here, we're starting at about no change in centigrade. This is not 0 degrees centigrade. This is percentage temperature change. Okay, so we're looking at change over time. This is not like a absolute value. This is a relative value. So start down here back in 1962. We go forward to 1990. You can already see it increasing. This is a quarter of a percent. This is 1% over here. Now into 2020, we're up 1.3, 1.52%. So you can see it's increasing at an increasing rate. So now we have a couple different observations here. We have the forecast, which is the red line. The observed value is the filled in blue line, and the upper confidence indicator or confidence interval is the green line. So the upper confidence interval is green. We have up to 3.2% change from where we are now. So that's a pretty big change. And the lower confidence interval is 1.73. That would be like the best case scenario. The Earth is not warming up too much, but the forecasted rate, the most likely, is about another 2.5%, a total 2.5% increase over where we started back in 1961. Okay, so I think that is kind of interesting. In this case down here, I'm looking at which countries have the biggest trends. I'm looking at the top 10 and then the bottom 10. So these numbers are the biggest. So these countries are probably in the worst spot to be in. Montenegro, Serbia, Salvador, never even heard of that one. Ukraine, and it goes down to Belarus. These are the top 10 worst, and these are the top 10 best. Namibia, Argentina, Sudan. So these countries will probably experience the biggest trend increase in average global warming, and these countries will probably see the least increase. And in a couple cases, I guess in two, maybe even like a negative increase, which would be a decrease, right? So these guys might not see much of a change of all, or a change in the opposite direction. But some of these countries, I think this is already like close to the equator, so it's pretty hot. So they're not going to notice much of a change. This country won't notice much of a change, but these countries right here are going to be impacted most significantly. Okay, so let's look at another angle here. So that was a linear change from where we are now to where we are going into the future. The second derivative of that is the rate of the change. So we see the change and then the acceleration or the deceleration. I don't think there's any deceleration here. I think it's only acceleration. But this is the second derivative, so it's not just the change, but how fast the change changes. Okay, so this is called second derivative. If you've taken calculus, I know you've had exposure to this. Even in finance, we get into that a little bit with convexity and duration in the bond market. So this is second derivative showing us the linear trend over time, and we can see we fit this quadratic model for each country and examine the coefficient of the squared term. So basically, temperatures were decreasing, but that trend has slowed or reversed, and it will now start to rise faster. Okay, so these countries were in a better shape a few years ago, but the trend is reversing, right? So this negative is turning around, and this is the acceleration factor. So this is the rate of the change. Okay, so this change is changing from a negative to a positive, and then we see the rate of change in the second column over here. Now, these changes for these countries down here are much lower, so they're not going to witness too much of a difference over time, where these countries right here most likely are going to get slammed by the effects of global warming. So let's continue with the analysis. I'm trying to, in this example, I'm trying to look at when will 50% of the countries of the world exceed 1.5 degree increase on average in Celsius changes. So I'm looking at three scenarios here: 1.5 Celsius, 2.0 Celsius, and 2.5 Celsius change. So I'm looking at, again, the melted data frame. You saw before we had wide format. We melted it and put it into a long format. So that is the basis for the analysis here. So when I run it, I see in 2023, we have about 55% of the countries around the world will experience a 1.5% increase in average temperature on a Celsius scale, not in Fahrenheit scale, right? And no countries experience a 2-degree change in Celsius, and none exceed a 2.5 degree change in Celsius, thankfully, right? And nothing shows up because the threshold hasn't been met. So if we don't reach that greater than 50% threshold, that comes right here. If it's not greater than 50%, then nothing gets put into these boxes. If you lower the threshold like 20, we might actually see something. I didn't try that. Let me see. Yeah, then we actually get 22% of the countries, 21%, and 21%. I think that's not a scary number. I think this is a much scarier number. That's why I picked 50. So that's a big change. So 55% of the countries in the data set had an average temperature greater than 1.5 degree compared to the historical baseline. So again, kind of scary stuff. And I'm not a climate expert, but I did a lot of research to put this together using Google, using ChatGPT. So I think this is pretty accurate, and I'm just applying common sense as well. And I think this kind of makes sense to me when I'm looking at it. So if there is some climate expert out there and you can confirm or deny, that's great. I'd love to hear from you. I did the analysis. I did the homework for this. I think it's mostly correct, but this is not my domain of expertise. I think it's an interesting problem to analyze. That's why I picked it for the lesson today. And I think it's mostly correct. If you find a mistake, let me know and I will fix it. Okay. But I think it's pretty darn accurate. So let's move on. Continuing here, using this melted data frame, again, going from wide, what you saw originally, to long. It just makes it easier to work with this data. Otherwise, you have to slice it up all kinds of crazy different ways. Once it's melted, it's just easy just to move through the data set and just do our normal analysis. So now I'm looking at clusters of countries and lag coefficient and then the rolling variance. So basically what this is looking at, again, trends over time. We can't just look at one point in time. It's abbreviated PIT. A pit is a point in time. We can't just look at one pit. We have to look at the trends and the changes over time. That's why we're looking at these rolling variances and the lag coefficient right here, okay? So basically, this is a classic early warning signal of climate change. So scientists use this, ecologists. It's useful for understanding system dynamics, anticipating runaway climate change and ecosystem collapse, or reaching some type of irreversible tipping point where we'll never recover from, right? So high lag closer to 1 means worse, lower is better. So these guys are kind of bad. This is really bad for this country. It's pretty bad. This is pretty bad. Lower is better. So this is not so bad in Zimbabwe. So that, I believe, is pretty close to the equator. It's already pretty hot. It might get a little bit hotter, but not too much hotter. For these guys over here, Western Sahara, actually pretty hot, but that's a pretty harsh environment, the Sahara Desert. So maybe the desert will expand and just grow and multiply by hundreds or maybe worse, maybe thousands of acres of lost land, farmland, or whatever. So for the lag AFC, higher is worse, lower is better. For the rolling variance, basically the bigger the number, the worse, and the smaller the number, the better. So bigger number means more intense or more unstable, wild swings in temperatures, and lower numbers mean less climate change, less volatility in the behavior of the temperature, or the change in the behavior of the temperature. So I thought this was interesting. I tried to do a hierarchical clustering of countries based on temperature change and the patterns of those change. Let me hit Control Enter. So on my channel, I've got a lot of videos about clustering. I think these are pretty interesting. So basically, we look at the distance, the measured distance between these data points, right, to figure out which countries go into which clusters and how much they change over time. So here's Afghanistan, Islamic Republic of Afghanistan, Africa. That's actually a continent, not a country. Probably should take that out, but I don't think it matters too much. Here's Albania, Algeria, Samoa, American Samoa. So we look at all these changes over time and then subtract it from the mathematical distance from what's above. So it's 0.0154 minus 0.075, and then 0.105 minus, which would be a plus, as you subtract the negative, 0.047. So that's the mathematics. So they look at all the changes and take the changes between the different countries to do the clustering. And then it looks like this when you plot it. Control Enter to run. There's my plot. The clustering is based on temperature change over time. So if we go back to the clustering over here, again, we're melting the data frame and we're looking at the year, okay, and the temperature. So that is what's used for the clusters, and I picked 4 clusters. There's a way to pick the optimal number of clusters using a silhouette method or an elbow technique. I didn't get into that. I looked at a couple different clusters. I think 4 makes sense. When you look at it on the map, you'll see a big yellow band somewhat close to the equator, certainly follows the equator, but it's a little above and a little bit below. All these countries are clustered together. They get into cluster 6. And again, this is the clusters of the countries are represented by the colors, right? So it's not change in temperature now. It's not Celsius change or anything like that. It's the clusters that these countries end up in that have the most similar change in temperature. That's how the measurement is done. So if we look here, we can zoom in on the country. I like these a lot. You can actually zoom in, right? If you push the mouse button down, and then you can zoom out. So I like these plotly chloropleth maps a lot. I use that a lot. So you can see basically the whole world here. This is cluster 1. Anything in blue is 1. So these have the same types of temperature changes. Anything in yellow is cluster 3, and these guys in Greenland and over here, Saudi Arabia, these have the most similar temperature changes over time. So remember, that's the metric that we're using. So it's not confusing. Any chart that you create should answer more questions and not create more questions. If you're showing charts to your stakeholders and they get confused and it creates a whole bunch of bewilderment and you're getting a lot of questions, the map is not doing its job. It should be pretty intuitive and pretty obvious what's going on. If not, then I mean, you have to get back to the drawing board and try again, or get some feedback and fix up the map. So or the chart, right? Like any chart that you create should answer questions and not create questions. That's what I'm trying to say here. Wait a second. Okay. So yeah, we're coming up to the finish line pretty soon. So now I'm looking at computing global average temperature change. Okay, again, looking at this melted data frame, and we are taking a linear regression model. I think that's appropriate in this case. The x variable is the independent, the y is the dependent. Just like before, the x is the year and the y is the temperature. We're not trying to predict the year, we're trying to predict temperature change. That should be pretty intuitive here. So the y is the target variable that we're trying to predict, and the independent variable that changes over time, but what we can't control is the year variable, right? So we've got that. We have our linear regression model, and I can go ahead and run it. So I think I just ran it, yes. And we have all the data saved up in here. So we have temperature BAU is business as usual. Business as usual if we do nothing. If we cut emissions just moderately, what kind of impact is that going to have? Okay, and if we actually meet the Paris Agreement cap, which is a huge cap on carbon emissions, then what would this scenario look like in the future? What would global temperatures look like in the future? So that's what we're trying to get to. Business as usual. Basically, we do nothing. Moderate cuts in global emissions, right, which is causing a lot of this global warming, most of it. I mean, there's other factors too. People say cow farts. I don't know how much of that is true. I've heard that from a few different sources, but I think most of it, by and large, comes from emissions. So if we cut emissions, or don't cut emissions, don't do anything. This is BAU, business as usual. Moderate cut to emissions. What kind of impact is that going to have on global average temperatures? And if we meet the Paris Agreement and cut emissions drastically, I don't see it happening anytime in the near future, but if somehow we're able to pull that off, we can see what the impact of that is. So this is the historical, the blue line is the actual historical global average temperature change. Okay, going back to 1990, I didn't go all the way back to 1961. You can do that. I didn't do that, but you can see it's rising quite a bit between 1990 and 2024. That's where we are now. Business as usual. We don't change any emissions cuts. Then temperatures are going to increase almost 5 degree average change in Celsius. That's pretty huge. You can see the increase has been pretty aggressive so far. If we have moderate cuts, then it decreases a little bit, but still increasing at an increasing rate. If we actually meet the agreements, the modifications agreed to in the Paris Accord, we can flatline this thing and have no more erratic or excessive CO2 emissions and no more excessive global warming. But realistically, is that going to happen? I doubt it. But maybe, I mean, that's the best case scenario, but not the most likely scenario. Let me show you one more thing that I found that I thought was pretty interesting. And I think we will see a cut in emissions in about 40 years, and I can prove it to you. But it's not going to be man-made, and it's not going to be willful. It's going to be necessary for other reasons. So this is called World Meter. I found this a little while back. I think it's pretty interesting. I think it's pretty accurate too. You can check the source for this information and how these numbers are derived. But just common sense, if you look at it, it says births this year, births today, deaths this year. I Googled this. Every year on average, globally, there's about 50 to 55 million deaths. We're at the beginning of June now, so halfway through the year. So this might be a little bit accelerated, but I think pretty close. Should be pretty accurate. So all these numbers are interesting. You have public health care, cars produced this year, bicycles produced this year, computers produced this year, 96 million. I don't want to get too far off topic. I'll get to the point really quick here. Just give me a minute. Money spent on video games today, 169 million just today. So that's a staggering number, 169 million spent on video games on just an average Wednesday. It's not even the weekend yet. Internet users in the world, emails sent. Okay, so a lot of pretty cool, interesting statistics. I'll show you what I'm getting to right here. CO2 emissions, so that's part of it. 16 billion tons of emissions this year. So that is a number that we really need to cut. If we can cut that and get that down to the Paris Agreement and flatline this sucker, maybe we have a chance. But even that is not what I think is going to happen. I'll show you what I think is going to happen. If you have a different opinion, you can put that in the comment section. So this is very interesting to me. So oil pumped today, 48 million barrels. Oil left in barrels, what was this? Million, billion, 1.3 trillion. Days till the end of oil. This, I thought, was the most interesting statistic of all. So we have about 38 years of oil supply until the Earth runs out of oil. Now, when the Earth runs out, we will stop emitting emissions because there's not going to be any more oil left. It's gone. But I have a theory we won't ever see the true end of oil because I think towards the end, the supply is going to be diminished so much, it's going to be so expensive, no one's even going to buy it anymore. Nobody in their right mind is going to pay $1 million to fill their gas tank, right? It's going to get so expensive at the end. We'll never truly run out, but in about 38 years, we're going to be essentially out of oil. So I think in 38 years, emissions are going to stop no matter what. So approximately 38, could be a little sooner, could be a little bit later. That is my hypothesis, okay? So I will wrap it up here. I'm going to put a little end stamp at the bottom. Oh, it's there. It's just hiding. Let's put end just so you know the end and not like, oh, was there more? Did I forget to do something? No, the end is the end. So that's it, guys. Just wanted to drop that knowledge on you. Did a lot of research for this one. I think it's pretty accurate. As always, if you find some mistakes, post it in the comment section. I'll take a look. If you have some comments, just general comments, post those. Hopefully nothing too negative. But I mean, like a little negative feedback is okay. If it's constructive, if it's destructive, then I don't necessarily want to hear about that. And that's it. So yeah, put a lot of effort into this one, a lot of labor went into it, and hopefully you guys enjoy it and learn a couple things about melting data frames, doing forecasts into the future using ARIMA and regression models and things like that. That was the whole point. So I'm going to wrap it up here, and I will see you guys in the next video. Goodbye.